ETH in Zurich. He works in VfB. And but his alma mater is Trento. He has a master in environmental engineering, I think, from Trento, and a PhD also from Trento. And well, David is a known person in the eco-hydro community. He has been. Are you having problems or? No. Okay. And he's well. He has some work. Also, many work published. He's active in IHR as well, in the eco-hydraulics community, and he has been working after his PhD in ETH Zurich and in ERVAG, and now in ETH Zurich again, always in Swiss. So, I think the floor is yours. You can start. Do you have 35, 40 minutes, right?
Okay, I will do my best to stick to the time.
Okay, thank you. No.
Thank you for the nice introduction. Thank you for having me here. I hope you can hear me properly also from online. So let's start. And I would like to just introduce what is eco-hydraulics. Just I don't know the whole audience, so I don't know if you are familiar with the term. I like this definition from Prof. Tinoco because it includes hydro-dynamic, ecological, and geomorphic processes. There is no general and established consensus of what is eco-hydraulics. It's still a growing field. You can have several more definitions in this website of the community, but I picked this one because I kind of like. And let me be indulgent with myself. Today I will talk about eco-hydraulics as a big definition, including also geomorphic processes. In literature, you can find different ways to especially stress links between vegetation and morphodynamic processes, for example. So you can find eco-morphodynamics, biomorphodynamics, eco-geomorphology, and blah, blah. I put this all together in the big family of eco-hydraulic research. It's in a steadily growing field of science, interdisciplinary field of science, and you can see from publication score, it's growing up and it's receiving more and more attention. Next year, we will have a joint symposium of eco-hydraulics together with Fish Passage in Canada, and also recently in the IHR World Congress, there was more and more sessions dedicated to eco-hydraulics, more than 4 or 5. So it's kind of an important and growing field. Within this, why also we have it can play a relevant role in maintaining and adapting ecosystem services, because we have different needs. On one side, energy transition and security. And technical solution to harmonize this type of different directives and needs. Within eco-hydraulics world, I'm working since several years in hydro-peaking that belongs to the category of alteration of flow regime. And we are also with Marcus here in the audience. We are collaborating at international scale to shed some more light and make more impact in the domain of hydro-peaking. If you are not familiar, just a rollback, what do we mean by hydro-peaking? This is holds true, especially if we move a bit upstream in more alpine context, but often we have upstream reservoir, penstock, and hydropower plants. So you can imagine that whenever we turn on our hydropower plants, we have to produce electricity, we have this wave of hydraulic wave traveling the downstream receiving water body. And this is just a time lapse of a river in Italy. So you can see that the ramping phase lasts 5 minutes. So you pass really from base flow to peak flow in very few minutes. As another example, we are still in Italy, and this is Noce River upstream of the big Santa Giustina Dam. So soil unimpaired catchment, and here we are below the dam. So you see my face, and you can see totally the natural regime is totally disrupted by this hydropower signal. And you can imagine this as a cascade of ecological consequences that are well known and studied, but still we have shed some light. We have to shed some light on several processes. And often due to this water fluctuation, we have also thermal fluctuation associated with a plethora of ecological impacts. Again, also in the sector of hydropeaking, there is a growing attention. We are building up a more strong community in last years. So there are several initiatives. We had a special issue dedicated on hydropeaking research, recently published it. And so it's also a growing domain of science in the big family of ecohydraulics. So this was just an introduction. I will focus today more on modeling. So how model approach can serve and help understanding and quantifying ecohydraulic processes. And so, of course, there are several challenges and opportunities. I would like to present a couple of examples in this aspect. I will start with a couple of overarching challenges, then we go to the specific example. And so far, the main challenge I encounter in my career in ecohydraulics is that we come from different domain, different skill, we have different language and different spatial and temporal scale of analysis. The first challenge is, of course, is develop a mutual understanding, a shared vocabulary, and finding way to work and do research on relevant and common spatial and temporal scales. This is one of the more social challenge, let's say, but it's of key relevance. A second overarching challenge. Can I move? It's annoying, but the second overarching challenge is for myself as a developer of numerical models is that this is the wish-to-do list when we develop our eco-morphodynamic models. So there we want them to be accurate and efficient. We want to benchmark with analytical solution. We want them to be fast and also to be ready for usage. But these are also the challenges that often, especially in alpine context, we have to deal with fast transient flow, with wet and dry interfaces that complicates a lot the solution of our equations. We have shallow flows from centimeters to meters. To match the ecological scale, often we have to use hundreds of thousands of computational cells because we are interested in scales that are meaningful for ecological processes. Saying that, I would like to jump to these three examples I prepared for today. So the first one is regarding fine sediment dynamics, the second seed establishment, and the third one fish stranding. Again, to stress a bit how modeling approaches can help in solving data in this problem. So fine sediment dynamics, I anticipate that I use this example just an excuse to present a bit a numerical solution that helps solving this type of problem. So I will dig a bit slightly more into mathematics, applied mathematics, but this is just the first example. Then it's easier with less math, let's say. But so here we are, I think more or less here now. If we go upstream in the Rhine, upstream in the Bodensee, we have this channelized part of the Rhine River flowing to the Bodensee, and there is an ongoing international project to restore the river, widen the channel. Mostly, the main objective is to improve the flood safety, but of course, when you manipulate and change river, there are multiple processes to be accounted for. So here we have a rendering. This is how it looks today upstream of the Bodensee, and this is just a rendering of what they expect in terms of evolution of the floodplain with way more natural processes and natural features building up in the river. In particular, what is of concern are the dynamics of fine sediment. If this is now the situation with this internal dig, we have evidence of fine deposition after the floods. They are wondering, okay, if we widen our river, what is going on in terms of dynamics, deposition and erosion of this fine sediment, and how these interact with floodplain vegetation. It's a well-known problem. Also, Mario spent several years investigating this issue. So, in a very simplified way, we have compound channel with a floodplain, and we have particular pattern of flow velocity generating also a shear stress that influence the exchange of fluxes between the main channel and the floodplain. And if we focus on the modeling approach to model these case studies of in the Rhine River, we need to put together different modules. We have an hydrodynamic module that we apply. We need a turbulence module to catch this shear layer, and then if we add the sediment transport, we have different features, but for sure to model suspended load, we need this advection diffusion equation. And if we then want to interact to investigate the interaction with vegetation, we need more features. I will touch briefly on this. We have a module dedicated for this in our in-house software that we develop, basements that we develop at ETH. As I mentioned, this was just an excuse to present a numerical solution we were proposing to efficiently solve this problem. And so to simulate suspended load, we have to solve this advection diffusion equation where it's kind of classical form. We have a concentration we want to integrate over time and space, and we have these two advection and diffusion component. And it doesn't matter the other part of the equation. When we solve the turbulence model, we have kind of the same component. And when we use a K epsilon turbulence model, we'll have again kind of a diffusion term emerging from the equation. So the goal here is how to solve this in an efficient way using common and standard hydrodynamic solvers. And before this project, we were developing a solution, a numerical solution to try to resolve efficiently this type of problem. So whenever we have an advection diffusion problem, we have an advection term, an diffusion term, how to solve it efficiently. So here we have a shallow water equation plus the advection and diffusion of the whatever passive transport type. And so just briefly to explain the concept, this partial differentiation equation system has a parabolic nature due to this diffusion term that if you want end up with what's so-called the infinite speed paradox, in the sense that the information due to the diffusive term travel with infinite speed. And so of course this is a simplification, but you can imagine that the parameter space of space and time, you have the lambda, so the speed of information traveling with infinite speed. This is a bad use, of course, when we want to integrate in a wave style our equation, as we do with hydrodynamic solver, because our time step, integration time step, for stability reason, will go to zero if we have information that travel with infinite speed. So we use an old concept, actually nothing new, but we apply it to this framework, 2D framework for advection diffusion, called the relaxation approach. So we we introduce a relaxation times epsilon and auxiliary variable psi that actually tends to the derivative of our concentration, that is our term that is diffused as epsilon goes to 0, and we insert an evolution equation that is more or less an advection of these quantities here plus this stiff source term. If we play with this mathematical model, we end up in a system that is fully hyperbolic. So we start, of course, we are adding some equation, but this system of equation is now hyperbolic with this ad hoc relaxation, and it's equivalent to the original system in the case of epsilon tending to 0, and for steady state for all the epsilon. Of course, now we are playing with math in the sense that now we have another system is no more the original, so we are solving numerically this relaxation system that is different formally for any finite volume of epsilon. So the difference between the original and relaxation is the formulation error. The tricky point now, or the opportunity, is that if you find an optimal value for this relaxation to limit this relaxation time, you can have something that is useful for and meaningful from a numerical perspective. And authors before us, they were proposing a threshold that scale with the cell dimension of your problem in the order of accuracy. So to say, if we keep this relaxation error or this relaxation term smaller than this threshold, actually the formulation error we introduce in the system is smaller than the numerical error. It means that if we refine our mesh or we increase our order of accuracy, we can ensure that actually our numerical model is converging back to the original model. So we are happy we stay in this area. So the formulation is smaller than the numerical error that in any case we will commit. Of course, if we are here, we are in trouble. If we implemented this in basement actually, so we were able to solve many problems related to advection diffusion, so fine sediment transport, but also temperature, advection diffusion of temperature, or pollutant transport in general, without almost losing efficiency in terms of simulation time. And this was the main goal, and this original paper on this method. So going back to our example, we implement this, we were able to solve kind of in this large scale this problem. So testing our fine sediment simulation, we test different T50 representative diameter for our flat plane. And here you see just a sketch, this kind of sensitivity analysis of the deposition area by changing the diameter. And then we had our scenarios model, and we end up with some suggestion and conclusion. We saw that there is no significant effect, for example, in terms of flood safety with this deposition of fine sediment. We also went a bit further and test the interaction of fine sediment with vegetation, thanks to a vegetation model that we developed that I will briefly introduce in the next example. So that was the first example, how numerical strategies can aid and support and allows for large scale eco-hydraulic application. I jump now to the second example related to the seed establishment. Here the focus is more on interaction between riparian vegetation and hydrodynamics. It's well known that riparian vegetation has several critical ecosystem services, and there are several researchers and group of research focusing on the interaction, mutual interaction between hydromorphology and vegetation. So how hydromorphological condition influence vegetation, but also how vegetation influence hydromorphology. It's a mutual feedback. We had a module also for this in Basin. Now in this example, I was focusing a simple phase of, so not in a mutual feedback, but just on the seed dispersal. So that it's mostly driven by hydromorphological condition, but there is no explicit feedback. So it's a simplified model. And this is the full model I was mentioning, where we can actually simulate the mutual interaction between hydrodynamics and vegetation, considering also a vegetation growth phase. But this, again, is a different part of the story. This example, I would like to focus only on seed dispersal and establishment and how this is influenced by hydropeaking. And it's well known that, I mean, if you compare a free-flowing river without hydropeaking, you might have influence on the vegetation dynamics, the shoreline, where actually this hydropeaking signal is active. So we move a bit upstream. We are in the channelized part of the Rhine River with this nice and interesting pattern of alternate bars. And there is this evidence, these alternate bars, so this sediment, deposition of sediment, they have some vegetation dynamics. And today about 25% of the area is covered by vegetation, and we were wondering what is the role of hydropeaking in the seed establishment in this part. So we employed a simple model based on windows of opportunity for vegetation establishment that works in this way. So we have bank, and you can imagine we have these two seeds that actually establish in the river. And they establish because of they are drag and deposit there because of flow fluctuation. So during the recession phase of an hydrograph, you have the deposition of this guy P1 here, and then during this recession phase of this P2, and then they can develop and grow in time. And the first one is lucky, start develop resistance, and because of his position in the floodplain and his characteristic can develop resistance quicker than the following disturbance represented by the following inundation period. The second guy is less lucky, so it starts terminating, developing resistance, but then the following disturbances are higher than the resistance, so this seed here will die and washed away. So it's a very simple model that it collects just some key processes of seed establishment. We can model different type of vegetation resistance to make it easy. Let's say we call high resistant or fast growing vegetation, so they develop quicker resistance in time against low resistance, slow growing vegetation. And this sketch is just to show that the model represents well what is happening here. We have this successful rate, so we count the successful establishment event over the total establishment event, and you see this with this shaded area. It represents fairly well where actually vegetation is distributed in our bar. It's just a visual plot to show that actually we can visualize spatially our result. And then we were testing what is happening with hydropeaking. So here we have our hydrograph, and if we zoom in, we have this typical pattern of hydropeaking. We actually use a synthetic version because we want to manipulate and try to change the base flow, the peak flow. So we design a synthetic hydrograph based on the existing one. And we test several scenarios. Here, just to simplify the reading, here we will have the different scenario. We will look at it's a percentage what we look at. It's the successful establishment area over the total bar area. So we have the original scenario. This guy here, it corresponds basically to the original scenario, but it's the synthetic one. So we have base flow plus existing hydro peaking. Then we manipulate several. We have several scenarios. We investigate just the base flow. We get rid of hydro peaking, and we increase the base flow. We decrease it. We modulate with season, and then we keep the same base flow, and we change hydro peaking. We increase the peak level of hydro peaking just to understand what's happening. And then we have two types of vegetation. And these are the results, and I don't want to go through all these results, but already this module, this simple model tells us some relevant information. For example, the first one is that actually the influence of base flow in terms of potential vegetation of our bar, if you look at this value plus 30%, this value minus 30%, so the variation, if you modulate the base flow, it's way more important than if you change the peak production. And this also suggests that the hydrological year is way more relevant than the production peak in this context. Of course, we cannot generalize. So if we have a wetted year with higher base flow or a drier year with lower, it can impact more the final results. And yes, again, this we can see that the marginal difference is very small. Of course, we have a reduction of vegetated area, but we have to increase a lot the peak to observe actually the variation. And all these symbols are the average of over all the bars. And that was the second example how we can use a modeling approach for approaching eco-hydraulics processes. Last one, we move to a smaller scale. We talk about fish stranding. It's again mostly related to hydro peaking. It's actually a natural process. So fish gets stranded after a natural flood, but it's way more a critical problem in case of hydro peaking. It's known that ramping rate affects the fish drift, and it's also known that ramping rate in some way influences directly the amount of fish that gets stranded. Here we want to try to provide and develop a tool to serve a more fine scale modeling of different scenarios for restoration purposes. So together with colleagues from another institute, Stoker Lab at Environmental Engineering Institute at ETH, we are developing this model that we call fish escaping routes. It's composed by three main parts. First, we identify escaping route for fish when the flow is changing. Then we assess the suitability of this pathway. Then there is a third phase, that is result processing, and we use 2D hydrodynamic maps, let's say, or solution from Basin or whatever solver as input, and then we have some other biological inputs to the model. And if we have a look how it works, we are in a recession phase. So the discharge is decreasing from Q1 to Q3. If we look at in a river section, we have a decreasing of the water table. We can visualize all in this overlay raster. So we have suitable habitat for a given fish at different discharge, Q1, Q2, and Q3. So in the first step, we have some assumption that the river is sitting in a suitable habitat, and the fish will look for and scout for suitable habitat during the recession phase. These are kind of biological assumption. So we find out all the possible paths connecting suitable habitats at different discharges. And then we assume also that fish among this potential path connecting this will choose the best one. And so we will pick the best route. Then for all the cell, we will identify this best route. And then we will do the same with the resection of the discharge. And sometimes there is no more physical connection with the following habitat. So you have a stranding event. This way, we actually identify all the possible escaping routes for these down-ramping events, but still we don't know if these are suitable. So if we focus on one route, we can analyze if this is actually suitable for the fish. So the fish wants to follow this route, but the flow is going in some other direction. So actually, this effective velocity of the traveling of the fish is it's a component, a vector component between the velocity of the flow plus actually the fish velocity. Then we have some constraints. So this effective velocity should be larger than or equal to the velocity of this route. Otherwise, the fish is too slow to reach the new habitat. But also, this swimming capacity should be smaller than some critical biological threshold. Otherwise, the fish is not able to cope with such strong current and it will drift. So with a non-controlled behavior. So we can also implement all these limitations in terms of critical velocity, and we end up just with some successful pathway connecting habitat. And then we can upscale the result in terms of indicator using kind of an habitat approach, where we say, for example, we are evaluating different type of indicators, but for example, here we are proposing this weighted habitat loss, where we have a suitability of different habitat. It's kind of a standard form, but actually we have percentage loss because we evaluate all the possible path, the suitability of all the possible path over actually the disconnected path. So we end up with the integral indicator where if it's 0, it means we don't lose any path in this variation of discharge. So we don't lose any habitat connection, or 1, it means we are, whatever habitat they are connected are lost in this down-ramping phase. So we have no connection, or if you allow me the highest strength is. We were testing this approach in this figure where we have different morphologies. So here we have the release of hydropower plant. We are close to Interlaken in central Switzerland. We have this Buhnen, this growing elements that are actually done to increase the or decrease the impact, the ecological impact of hydro peaking. And we have a stretch with bars and the channelized stretch. And to show some results, we have target species. We were evaluating this habitat loss, and we can see we evaluate both up ramping and down ramping phase. From this preliminary analysis, it shows, for example, that actually this loss of habitat is actually minimized by this growing. So in this term, from this aspect, this growing element seems to have a favorable action and effects on reducing stranding risk. Of course, we are not here considering this piece of other elements like fine sediment dynamics and other issues that may impair the success of this feature. But with this, we can investigate which type of morphologies are performing well or worse in this with this aspect. Of course, advantages, but also challenges. We are still doing a lot of research. One of the biggest challenge in this type of models is that we don't have a lot of biological data. It's really difficult to collect data on fish trending in a consistent way to validate this type of models. There is a PhD working on it. And of course, we can include different rules to account for the fact that fish are not engineers. They made wrong choice. They have waiting time. They have delaying effect. So we cannot force them to do what we like. But it's still promising, and we hope that it can provide useful information in terms of hydro-peaking mitigation strategies. I have to conclude, right? Perfect, almost perfectly in time. Further challenges, we have a lot of models and we have a lot of skills, we have a lot of capabilities. What is still challenges in some way to put everything together, to connect the modeling framework. We have an urgent need to include also global warming in all this framework. Of course, it's all there, but often it's impacting different models in different domains, different level, and the cascade effect is here in rivers. It's not that easy to approach this. What I see in my experience that we still are not that efficient in river survey, in river topography, especially for the underwater part. I'm talking about more alpine rivers. In large rivers, potentially easy if you can go with a boat. With smaller rivers, it's a bit tricky. There is a gray area, and also the need for data collection and sharing, open data collection, sharing to build up and train and calibrate this modeling framework. And then, of course, we have bigger challenges. I mean, we have wars that impairs also energy production. There was cascading effect of the war, Ukrainian war on hydropower production in Switzerland. We have temperature that it's rising in all Swiss rivers, but also worldwide, I would say. We have to cope with non-stationary process more and more. And then we have plethora of other emerging processes, and it's also an opportunity for research in the field. To conclude, I'm going back to the initial slide. So let's take a message for us as researchers and scientists. Economics is rapidly developing an interdisciplinary field. We need to really foster interdisciplinarity in both research and education. That's my final words. Thank you very much.
Thank you. Okay, thank you very much, David, for this fascinating introduction to hydraulics. So now we have time for questions. The timing was perfect.